There it is. So section 5.4 is on the fundamental theorem of calculus, or FTC for short. So this is going to be the section that ties together what we've been doing with the limit of Riemann sums, with antiderivatives and all the derivative ideas from earlier in the semester. So it is going to connect integration and differentiation. Now let's not, there we go. And is going to enable us to compute integrals by using antiderivatives of the integrand function rather than taking the limits of the Riemann sums as we did earlier. I know you all enjoyed that long process of working with the limit of Riemann sums and trying to be like, okay, where's the formula for the first n squares being added together, et cetera, et cetera. Those ideas will show up a lot in Calculus 2 with sequences and series and just the ideas of convergence. But the antiderivative will allow us to shortcut many of those ideas. So we're just going to do a sampling ideas from this section. The mean value theorem for the definite integral, we're going to just state it, talk about what it means briefly, but we're not going to spend much time on the mean value theorem here. That would just be average. So the statement is as follows. If a function f, so if f is continuous on a closed interval a to b, then at some point c in the closed interval from a to b, we have the following statement, that the function evaluated at c is the average value. So 1 minus b over a times the integral from a to b of f of x dx. This looks probably very similar to the mean value theorem for derivatives, which basically the mean value theorem said that you had the some point c in the middle. Here, let me just go ahead and pull it up here for reference, actually, so you just to kind of relate it. So the mean value theorem for derivatives was this one right here. Essentially, if you have a secant line between A and B, then you would have a tangent line at some point C in between them. This is the analogous result with integrals. That is to say that the average value, so if you think about the average value is just when we essentially consider the water leveling, is going to be equal to the actual value of the function at some point. So it's just not a conversation about derivatives as much about the values of the function. So that's the mean value theorem for definite integrals. For those of you going to Cal 2, you'll explore this idea more. So the other idea is the fundamental theorem of calculus. It has two parts. Part one is something that we've stated informally, but we're just going to make it formal with this. And maybe at the end of class, there is, has anyone ever heard of Grant Sanderson's channel, 3 Blue, 1 Brown? So it is a fantastic channel where he does very high quality animations and explanations of math. And one of his is on the fundamental theorem of calculus. So it ties a lot of ideas together, so I want to leave some time to explain it because, again, it's nice because it has animations and he has a nice, calm, soothing voice I wish I had. If it wasn't Morgan Freeman, it would be this guy. So we'll look at him at the end, but let's go ahead and just state the fundamental theorem of calculus, the first part, highlight the important part, and we're going to spend more time looking at the second part, which allows us to shortcut the idea of the limit of Riemann sums from earlier. So here's the statement. I'll read it first. If f is continuous on the closed interval a to b, then capital F of x, which is just going to be integral, well, I'll write here in a moment, is continuous on that closed interval and differential on the interior, and its derivative is the lowercase f of x. So let me go ahead and write that. And so if f is continuous on the closed interval from a to b, then capital F of x, which is simply going to be an integral going from 0 to x of f of t dt, is continuous on closed interval a to b. Give everyone a moment to write. And I'll briefly say a word about what this capital F of x is. So this capital F of x is just going to be an integral, and this top part right here is going to be x, which allows for some movement on the x value, and f of t dt is just going to be some other function. So you can see that visualized down here below, that this right here is this area under the curve. And then this f of t is the actual function that is going to be the heights of some rectangles. So we'll tie these together a little bit later. So that's the first part. And is differentiable, and, hold on, f is continuous on to a to b. Okay, and is differentiable on open interval a to b, and its derivative is lowercase f of x. So let me go ahead and then write the equation. Capital F of x, and if you take its derivative, that would be the same thing as the lowercase f of x. So if you remember, if you kind of look at this notation right here, there is something in the middle, but when you take the derivative of an integral, you get back the original function. So that's what this is saying. When you take the derivative of an integral, you get back the original function. So in terms of the actual kind of symbolic, when you take the derivative of that integral from 0, actually, it doesn't have to be 0. Little correction here. It could go from any starting point. So let's just say from a to x. So let's add a little slant or a little bar next to that 0. It doesn't have to be 0, I should say. So the derivative of the integral from a to x of f of t dt is equal to what we already wrote. The main thing I want us to hold on for this course are these end parts. That is to say, when you take the derivative of an integral, you recover the original function. So this right here connects integrals and derivatives. We really already said that back in section 4.8, where we talked about antiderivatives, but this right here just makes it formal. The intuition and the geometric behind it we'll come back to at the end of the class. I want to kind of go through the weeds of the computations while you all still have as much energy as you'll have, and then we'll just sit back and relax and enjoy some of the intuition here at the end. So that's the first part, connects integrals and derivatives. And let's go ahead and skip this page. You'll talk more about this in Calculus 2. And talk about the fundamental theorem of calculus, which is really part 2, which is focusing on the evaluation of area. All right, so here is the statement for this, and then we'll get to the computations down below. So if, again, f is continuous on the closed interval from a to b, and f is any antiderivative of the lowercase f on that closed interval, then here's the evaluation part. The integral from a to b of f of x dx is capital F of b minus minus capital F of lowercase a. So this right here, before we had to do the limit of the Riemann sums, But this right here is saying all you really need to do is find the antiderivative and then plug in the endpoints, which is really amazing if you think about the idea of you are summing up a bunch of rectangles, and this theorem says all we really care about is where it starts and where it ends, and everything else in the middle just kind of falls into place. So we'll look at, like I said, we'll look at the geometric, some geometric animations of that in a few minutes. So this theorem allows us to calculate a definite integral by doing only two things. Step one, find the antiderivative, which is denoted with capital F of a lowercase f. So there's step one. Step two is just to do f of b minus f of a. Capital F of b minus capital F of a. So with this, the fundamental theorem of calculus allows us to view integration and differentiations as inverses of each other. So just to get some useful notation set down for us to kind of write through our computation, this f of b minus f of a, you can write this a couple of different ways. You may just see this as capital F of x, and then you'll have a right bracket, and then there will be f, or there will be the a and the b. Just kind of like you take the antiderivative, and then you'll just move the a and b from the integral over to this vertical bar. You may also have that it is completely enclosed. This is useful when you have like an order of operations, things you want to make sure you're keeping an eye on. Or if you're just feeling lazy, sometimes they'll even just put a vertical bar and not even hook it. So if you see a large vertical bar, that just means the same thing, is you're going to plug in the top, the higher b, and then you'll subtract f of a. So that's just a notational thing. Okay. There's the setup. Let's actually do some computation now. So next page, evaluate the integral. So instead of switching this to a Riemann sum and trying to use all those formulas from back that we did in section 5.1 and 5.2, and even the first part of 5.3, let's first find the antiderivative. So this is going to be x cubed over 3 minus 2 times x squared over 2 plus 3 times x. And then what we're going to do is we're going to evaluate that from -1 to 1. Maybe something I should have said on the last page, but I'll just go ahead and say it here. When we took the antiderivative, what did we need to tack on at the end? Plus c. But no need to turn there. Let me just kind of call it out. Realize if you tack on plus c here and a plus c here, look what happens. You're going to subtract it. So that's why it says any antiderivative, because when you do the subtraction, the c's are going to cancel. That's why I'm not putting plus c right here. Because when we actually do the subtraction, the c's will cancel out. Okay. So the way I usually like to set up this computation is I'm going to go ahead and put a big parentheses on the left, and then I'll subtract and put a big parentheses on the right. I don't want this to bleed over, so let me just kind of... So this first parentheses is going to be f of a. So what I'm going to do is I'm going to do 1 cubed over 3. I'm going to just pre-cancel this. So I'm going to just cancel those 2's kind of early. And then we'll have minus 1 squared plus 3 times 1. That right there is f of a. No, excuse me, f of b. So this is b, this is a. So what I have right here is f of b. Then we're going to subtract f of a. So f of a is going to use the lower endpoint. So this is going to be a -1 cubed divided by 3 minus a minus 1 squared plus 3 times minus 1. So when I set up those parentheses beforehand, it's just because we're going to have a lot of numbers, and it just kind of helps me to kind of sort out the problem as I go through it. Any questions on what's there in red, or we good? Okay. So from here, this is just an arithmetic problem. You're like, finally, arithmetic, I could add. So this will be 1/3 minus 1 plus 3. Be careful with this second parentheses, because this negative will need to distribute if you don't simplify everything inside first. So this will be minus 1/3. This will be minus 1. This will be minus 3. So this is going to be, let's see, 1/3 plus 2 minus a minus 1/3 minus 4, which is going to give you 1/3 plus 2 plus 1/3 plus 4, or ultimately 6, well, let's approximately 6.67. So that is the second part of the fundamental theorem calculus, which allows you just to go ahead and find the antiderivative, plug in the endpoints, and do some subtraction instead of doing the whole limit problem we did earlier. Sorry for making you go through it. It was for your growth. Questions on this? Cool. All right, let's go ahead and look at this next one right here. So the first thing, you're going to take the antiderivative of cosine, which is anyone? It is not a negative sign, positive sign. And then you're going to evaluate that at 0 and pi. So you'll just end up with sine of pi minus sine of 0, which is going to be a 0 minus 0, which is 0. So I want to use this as an example to kind of think about, what does that answer mean? So any ideas why an answer would be 0? Emma? Yeah. So again, this right here is giving us the signed area. So the positive one will have a positive sign, and the lower will have a negative sign. So if we were to visualize this cosine function, that was exactly right, Emma. You'll have part of it below. So this is going to be from 0 to pi. So you can see this part is going to be the same as this. So there's a cancellation of areas, which is why we have the answer of 0. You have the same amount above and below. My picture was a little off, but as long as you're just considering that the integral is giving you signed area. So any questions on 16? Okay. Then 7 and 8 are going to be similar in computation. Let me go ahead and just kind of remind you the antiderivative, and then I'll hand over the problem to you to try while I take attendance. So the antiderivative here, the 3/2, well, let me write it let me just do 2 steps. If you're not sure, especially when it comes to like the square roots and negative powers, it might be worthwhile just to go ahead and be like, okay, 3/2 x to the 1/2 minus 4x to the minus 2 dx. Just rewrite it using some powers, so that when you go ahead and take the antiderivative, 3/2, then you multiply that by 1 over 1/2 plus 1, x to the 1/2 plus 1. Remember, it's the antiderivative, so instead of subtracting 1, we're going to add 1. Then we'll have minus 4 just comes down. And then we have the, 1 over a minus 2, the power plus 1, and then we have x to the minus 2 plus 1. So that right there is the antiderivative. So I'm going to give you a moment to see if you could just kind of understand that f of b minus f of a. And again, that vertical bar notation just says, I'm going to go ahead and plug in 4, and then plug in 1 and subtract. This is a scenario where I would actually probably do the whole thing just to emphasize that all of that blue is what numbers need to be plugged into. Let me give you a moment just to process what we've done, and if anyone has a question, let me know. Let me take attendance, and then we'll go from there. If you're having trouble, I have the work up there on the screen. Let me just give everyone a moment to just kind of check their work, process, and just see if anyone has any questions. Does anyone want me to talk through anything? Talk through it? I'm going to talk through it just to help out anyone who's maybe just kind of still kind of overwhelmed by the number of numbers on the screen. So are there any questions up to this point? Let me check here. Okay. So the way I approach this is I just simplify the fractions. 1 plus 1/2 is 3/2. And then same principle, -2 plus 1 is going to give me a -1. So then you could do some multiplication by the reciprocal. So this is 2/3. So ultimately that cancels, goes away. Negative and negative ends up with a positive. And then I'm going to send this x back to the denominator to get rid of the negative exponent. So right here, all of this is just capital F of 4. I just plugged 4 into both of these. And same thing, this is capital F of 1. I just plugged 1 into both of those x's, and we got that. From here, remember that 3 to the 1/2 power is the same thing as the cubed root of, let's see, hold on. It's the square root of, wow, I'll get this right. The square root of 4 all cubed. So the square root of 4 is 2. Cubing it gives us the 8. 4 over 4 is 1. So there's the 9. And this is 1 and this is 4. So we end up with 9 minus 5, which is ultimately just 4. So any questions on number 7? Okay, so this is again kind of pulling back ideas from the derivatives. We haven't done much with derivatives or antiderivatives. So does anyone think they know the antiderivative of this right here? Actually, before I say it, there is a little typo here. You shouldn't have dx here twice. What you should have up here in the top is just going to be a 1. So that wasn't anything new, that was just a typo in the notes. So what we need here is the antiderivative of 1 over x plus 1. Anyone, any ideas what was the original function that we had right here? It's really quite natural. ln of x plus 1. I like watching everyone's light bulbs come on when it's like, wait a second. Yeah. Very good. So the antiderivative is the ln of x plus 1. But remember that whenever you take the antiderivative, you do need to consider the absolute value of the input. Just because ln's don't play nice with negatives, so you do need the absolute value, where in the original integrand, you don't have that restriction because there's no ln's. The domain of the original integrand was all reals. Well, with the exception of -1. Okay, so then we are going to evaluate this from 0 to 1. So we have the The ln, I have a lot of clash of lines here, so I'm going to use my L with a curl, of the absolute value of the 1 plus 1. And then we will subtract from that the ln of the absolute value of 0 plus 1. So this is just going to be ln of, let's see, 2 minus ln of 0. Remember that the ln of 0 is going to, got ahead of myself. The ln of 1 and the ln of 1 is 0. So the answer is ln of 2 minus 0, or just simply ln of 2. So that is the evaluation of the definite integral from 0 to 1 of 1 over x plus 1. Anyone have any questions on that one? Okay. All right, so one last idea to make sure we solidify like the computational part, and then we'll go back and we'll watch that video to just get some of the intuition, and it ties it all back together in a relaxing 10 minutes. Hopefully it doesn't put anyone to sleep. I see a lot of tired eyes out there, but I think it'll be very helpful just to kind of see everything put together nicely. So the last idea, just to emphasize what those numbers mean. To find the area between the graph and the x-axis over some closed interval, there's 3 steps. Subdivide that closed interval at the zeros. Again, remember, zeros is just another word for the x-intercepts. So you can see right here, if we're looking at sine of x, we have some positive area and we have some negative area. So we do need to, if we're asked to find the total area, we do need to subdivide it. So I think, Destiny, you asked the question that was really important end of last class is, why did I do this with a 1 over b minus a certain time and when did I do another? Be careful what you're asked for. If you're asked for the total area, that's where you're going to have to subdivide it. If you're asked just to evaluate the integral, then you just go ahead and don't have to subdivide it. If you're asked for like the average, that's when you have to also multiply by 1 over b minus a. So notice that each of these questions, just keep in mind if you could conceptually understand what you're evaluating, it does make it easier to set up and carry out the appropriate computation. So we're asked for the total area, and you see it over here. We have some positive area and some negative area. So what we need to do to get the area, we have to set up the first integral from 0 to pi of sine of x dx. And then we have to add to that the pi to 2 pi of sine of x dx. That will give you the total area. With the exception of, remember that if you don't have to do this at the beginning, but you should notice, because you're looking for area, if at any point you do get a negative evaluation, you do need to take the absolute value of it. So if you don't know that off the top of the head, notice that they just kind of noticed that right here when they evaluated that second piece. If you didn't know which one was negative, positive, just remember if you get a negative, take the absolute value. So, because we want total area, we don't want cancellation of areas. Does that make sense? Okay, I appreciate the head nods. Okay, so the antiderivative of sine is anyone? You always mess up the sign. That's why I'm asking the class. Just throw it out if you know it. Half and half of you. So it is going to be a negative cosine of x because it's the antiderivative. So yeah, the derivative of sine is cosine. The antiderivative is negative cosine. And we're going to evaluate that from 0 to pi. And then we're going to add to that, again, if you didn't know the absolute, that this was going to be negative, you probably wouldn't have the absolute value to begin with. But let's see, then you would go like minus cosine of x from pi to 2 pi. So this absolute value. Again, if you did not know it was absolute value, just make sure at the end you at least make it positive. All right. really from here is pretty much the same as what was before. I'll have minus cosine of pi minus a minus cosine of 0. So that's f of a. Then we're going to add to that the absolute value of the second area. So let's change this up. This is going to be minus cosine of 2 pi minus, hold on, what am I doing? Oh, yeah, we're good. Yeah, we're good. So this is going to be minus cosine of pi. Okay, so let's maybe just kind of specify what everything is. This is f of b minus f of a for the first integral, and this is f of b minus f of a for the second integral, and then this addition just comes down like so. So a lot happening there, but the final simplification is, let's see, this is going to be minus a minus 1 minus a minus positive 1. Oh boy, this is really something. And then we would have plus, and then this is minus a 1 minus a minus, hold on, that's 1, and then it's going to be a minus 1. All right, so yeah, there's a lot of little sign things to be careful with there. Just kind of thinking about your unit circle. So this should come out to be 4, though. So this will be 1 plus 1 plus, should bring you down the absolute values. And let's see how are our signs playing out here nicely. So this is going to be minus 1, and that's going to be minus 1. So thank goodness, it looks like I didn't mess up the signs. It's going to be 1 plus, or it's going to be 2 plus 2, which is ultimately 4, which is we were expecting because we have area of 2 at the top, area of 2 at the bottom, and we did it. How exhilarating. Any questions on that one? A little heavy with the trig, so just take your time and look through that later. Yeah, Raul.
So for like total area, would they always give you like a visual, like a graph, so that you know where to like make that partition?
Not necessarily. So I just didn't show it. So normally what I would do if I don't know the graph, I would not have the absolute value here. But when I got here, I would see like, oh, that's negative. And if I'm looking for area, I don't want negative. So I would that's where I would take the absolute value. So does that make sense? If you don't have the visualization, just don't worry about the absolute value. But if you see a negative at the end, make it positive before you add. Sure. All right, let me give you a moment to set up number 10. Just go ahead and set it up. I'll go ahead and put out the computation up and give you kind of a moment just to look at it. But what I want to go ahead and do is just kind of take a step back and look at the big picture. And I'm going to borrow from another video to kind of help us look at nice visualization of it. So up on the screen, I have the full work. If you didn't get to it, that's fine. It's a little bit grindy of a computation that will take some practice. But I did want to go ahead and illustrate kind of the question that you posed, Raul. Like you can see right here, I did not put any absolute values until at the end here where I see that negative. And that's when I would be like, oh, I'm wanting the total area. So because the antiderivative, or because the integral is giving me signed area, if I see a negative and I want total area, I will go ahead and add it at that point. Does that make sense? Perfect. Question in the back. Yeah, Weston.
Without that, how would you know to make it like the intersection like at 0?
Yeah, so you would have to find the zeros. So you would have to set it equal to 0 and solve it. So if you didn't have this, what you would have to do maybe, and this is kind of more of a pre-calculus concept, but what you would do is you would take the x cubed minus x squared minus 2x, set this equal to 0, factor out the x, end up with x squared minus x minus 1 equal to 0, which would be x is equal then to factoring this as, oh, this should be minus 2, excuse me. So that's better because that's going to be minus 2 and x plus 1. So x is equal to 0, 2, and minus 1. And then you can see that's how we broke it up based off of the zeros. So you would have to find the zeros, you would order them and consider them within the interval right there. Does that answer your question? Yeah. Any other questions? All right. So we've been a little bit in the weeds a lot today. So we've made a lot of progress, but it is always nice just to kind of see how this chapter has come together. So I'm not going to show the whole video, and I would encourage you to watch the whole one, but feel free to just kind of step back, and I'm going to go ahead and pull up this video, and we're going to watch about 10 minutes of it, and that will wrap up our look at section 5.4. So let me go ahead and pull that up. He has many different videos, so I'm going to just do this one. Let me see if I can find where I put it. I'm going to stop the recording, so because this is, you could just